Okay. We are ready for more? All right. This is based on our calculation by using the formulas. We know that for our section LP is 5.7 meters, LR is 19.5 meters. The beam is like 1.8 meters deep. So the numbers are big. For LP is equal to 5.7. So if you can recall the first case in the middle, the unbraced length is 4.5 meters. So no problem. You're going to get the full strength, which is RPG multiplied by Fy multiplied by Sx. Because the unbraced length is less than LP, right? But for the 9 meter section, unbraced length is greater than 5.7 meters. But we have CB equal to 1.53, and this is in the inelastic region. So I use this formula, and this is the old approach. We calculate the critical buckling stress of the beam, and because this is SM400 plate for the beam, turns out that CB help boost the critical buckling stress beyond Fy. So by CB, we reach F critical equal to Fy as well, and we have the moment capacity equal to just that section, okay, because of CB. Otherwise, you will not pass. All right, you want this now or you don't want it? This is the design of the tension field action. Can you still take some more? Yes? Okay, good. Back to drawing board. Let me show you this first. The last slide. This is the drawing at the end. Generally, the plate girder stands on some support. So maybe this is where the bearing plate is, and this is just the portion that extends beyond the support. So in fact, the support is here, okay? And the panel attached to the support, this panel is called the end panel. We cannot use the end panel, the tension field action with the end panel, because this is the free end. So you cannot really restrain this panel. So tension field action is not allowed here because it's just gonna dance at the end. So we need to calculate the size of the end panel so that it is small enough that the buckling of the shear will not affect the shear strength of the panel. But for the rest, you can just use the tension field action. So that is why I can have a large panel for the internal panels, okay? So for the end panel, we cannot utilize the tension field action. And so the calculation is based on how much panel, or what is the size of the panel that I should use, okay? And before anything, let's say we begin by assuming KV equal to 5, because we don't know anything. We don't have any design for the tension field action yet, so it's good to begin with KV equal to 5. Let's assume we don't have anything. So I will plug in KV equal to 5 here, and see this limit, because of the thin web, it exceeds this. And when I calculate this, I should have changed this into CV2, I'm sorry. So I have to use the elastic formula for CV2, not CV1. This must be CV2, okay? So that means if I don't do anything, if I don't create the end panel, that web can only carry shear up to 12 tons, which is far less than the value of the reaction, which is almost 100 tons. So we need to design the end panel. And I have to assume this by back calculating it. This is the old approach, so I need to satisfy this ratio. So in the end, I try the size of the panel. And when I try the size, I have the A over H ratio, and then I now can calculate my real KV, because I am going to use the stiffness to create the panel. That means kV can be calculated by using this formula. If you don't have stiffness, kV is going to be 5. Now, if I have stiffness, I can calculate kV, and kV now becomes 15.5. And I can recalculate the limit. Now I have the CV. For the interior panels, I can have this strength with the tension field action. I don't know where is it gone. I missed that. I didn't include the calculation of the end panel, but the size shown here should be enough for the shear. My apologies. I may look for it tonight and I'll show you tomorrow. But here, after the design, this is the interior panel with tension field action. I can try this size. I can calculate CV2, and then I can use this formula to calculate the tension field action with that extra term, and which brings the shear strength up to 126 tons. So with tension field action, we can design the web to undertake that much shear. Okay? And that is why we can use the thin web for the beam if we know how to provide the stiffness and design the panels with tension field action. Okay. That's it for today. If you have any questions, it's time to ask them now. Oh, it's a bit tiring, yeah. Right. Okay. I think so. Nobody wants to ask any more questions. They just want to go home. Believe you me. Yeah. Right. Yes. Thank you for today.